Alright, welcome to Physics 2211 Lab 5. My name is Sophion Mongo, and the purpose of this lab, I did the falling slinky for the Choose Your Own Adventure, and the purpose of this one is to observe the motion of a slinky drop from rest, and to model it as well in GlowScript. And here I have a brief preview of the results that were obtained from this lab. The motion of the slinky is graphed right here, and you can see in red it was the motion from GlowScript, and green was the motion from Tracker. They do differ a little bit, and we'll be getting more into that later, but brief previews right here. Moving on, we have the concepts used in this lab. Momentum principle was the primary principle used in this lab. F net is equal to change in momentum over change in time. And from there, we can also derive the position update formula and the velocity update formula. And furthermore, some forces, the predominant forces in this lab that we accounted for were the force of gravity, mg, and then the y hat vector for the direction, and then the force of drag, which is a proportionality constant times the magnitude of the velocity squared, also multiplied by the direction of the velocity vector. And moving on, we have our tracker video right here, and this is me plotting starting from the bottom of the spring, just plotting as it fell. And the system was if I say spring, I really mean Slinky. I just keep mixing the two, but the system was Slinky and Earth, and the surroundings was everything else. And the initial conditions that we also obtained from Tracker, mass was 0.25 grams, and the initial position is negative 0.01133 in the x direction and negative 1.226 in the y direction. And the velocity as it starts from rest is 0 meters per second, and the time elapsed for the Slinky to fall when released was 0.44 seconds. And here I have my GlowScript code, and the changes that I made predominantly are highlighted. Adding the mass, adding the initial position and velocity, the time is 0 and then doing the time step, and the gravitational constant, and the proportionality constant as well. And then I have my first calculation loop right here. This is when the bottom of the slinky is not moving at all, and when the force of tension and the force of gravity are equal and opposite, the tension of the slinky pulling up from like the rest of the tension on the bottom of the slinky from the rest of the slinky above it pulling it up, and the force of gravity pulling it down, equal and opposite. That's what's being accounted for in the first calculation loop, and in the second calculation loop is when the slinky gets bundled together and actually starts, the bottom of it actually starts falling. And here we're accounting for gravity and drag, and then we plot do the velocity and position update and plot that as well. And here are the results from this lab. You can see the motion graphed right here. In red we have GlowScript, and in green we have Tracker. They're pretty similar, but you can see the Tracker has a more extreme slope. Well, I say extreme, it's not that extreme, but it's more so than the GlowScript one. And it may seem like quite a large difference, but the scale isn't as heavy either for the y direction or y axis. But there is slight differences, and we'll get into some sources of error as to why this could be. So some sources of error that we have error using the Tracker software. Actually, putting the points on the bottom of the slinky as it's falling, I could have messed that up a little bit, and it could have caused some deviation in the data. We may have had the incorrect mass of the slinky, and furthermore, there could be more forces acting on the slinky that we did not account for in our GlowScript model. And also for the GlowScript model, the proportionality constant for the drag force, I used guess and check to estimate it. I could have had that wrong as well, and that could have affected the data. And for the what does it mean question, as you can see from the Tracker video, the bottom of the slinky stays stationary as it's falling, and this is due to the force of tension acting on the bottom of the slinky because of the rest of the slinky that's pulling it up, and the force of gravity that's pulling it down, and they're equal and opposite, so the bottom of the slinky stays stationary as the rest of it's falling on top. And then once it all kind of gets bundled together, there's less tension, so the bottom of the slinky and then the slinky altogether starts falling, and we count for drag as well. And that's when we have the second calculation loop and everything. And that'll be it for this lab. That was all. Thank you so much for watching.